Hey guys, so this is going to be a short video looking at one topic, inductors. And I'm going to present this basically in analogy to capacitors. We don't have enough time to go into a lot of detail, so we'll kind of rely on what we know about capacitors to give us some insights. So, uh, similar to capacitors, an inductor can be a energy storage device in a circuit. Um, so remember, we thought of capacitors as basically devices that stored charge as a function of voltage applied to them. And now that we've been working with currents and we've been working with magnetic fields, and we know that magnetic fields are generated by currents, you can think of an inductor as a device that stores magnetic flux as a function of current. And the proportionality between the flux and the current is the inductance. So, and the unit for inductance is the Henry. And you'll notice this looks quite similar to Faraday's law. So we know also that an EMF, we take a derivative of this, is caused by a time-changing flux, magnetic flux. So if we know that these things are the same, and the inductance is a characteristic of the geometry of the configuration, and it's not going to change in time, then this becomes equal to the change in time of the current. So in other words, if you have inductance, a changing current will cause there to be an EMF, will cause a voltage. So, you know, if you have a large inductance, or if you have, you know, a sudden change in current, then this means that this will cause an EMF, cause a voltage. Now, and actually, this is behind why, like if you have a circuit, so suppose you have a circuit here that has a lot of inductance, and suppose the circuit starts closed, and then you open it. That change in current, by disrupting the flow of current, right? You've gone from current to nothing, will mean that there will be a big voltage that's generated. And so that can cause there to be a spark on your switch, and that's part of what degrades things like switches in circuits that have a lot of inductance. So that would be something that you'd have to be aware of when designing such a circuit. So continuing our analogy to capacitors, remember we talked about this energy stored in a capacitor. It looks like 1/2 CV squared, among other ways of expressing this. Well, for inductors, it is similar. The energy looks like 1/2 Li squared. And then, you know, our sort of prototypical system for talking about capacitors was the parallel plate capacitor. So, and we use this for, you know, for everything. Actually, let me draw this again. So this parallel plate capacitor was kind of the archetype for our model of a capacitor. And the go-to system for when we talk about inductors is a solenoid. So let's derive the inductance for a solenoid. Actually, let me draw this a little bit better to give you a better idea. So we've talked about the magnetic field inside of a solenoid. And so what's going to be relevant for us in this situation is we need the length of the solenoid. You know, if we were looking at this on end, it would just be a coil that has some area. We need the area because we're going to be talking about magnetic flux. And you know, we would need the number of turns also in the solenoid. So let's derive its the inductance. So going back to where we started this conversation, the amount of flux is going to be proportional to the current via the inductance. So in other words, the inductance is going to equal N times the flux over the current. Well, if we're talking about a solenoid, the magnetic flux is going to be equal to the area of the solenoid times the magnetic field in the solenoid. And the magnetic field in the solenoid is mu naught. So this will be mu naught times N over L times I. So that's the flux. If we put that in here, then we see that this is down here. We have N over I times and we can see that the that factor of current is going to drop out. And so we're left with the inductance for a solenoid being equal to mu naught N squared times the area over the length. So notice this only depends on the configuration. It doesn't depend on the current. It's just a function of the the dimensions, the geometry and stuff, as well as the it depends on the constant, the permeability. So, and I should mention, analogous to when we were talking about capacitors, remember we looked at how you could modify the capacitor by increasing the permittivity to some relative permittivity where it was, some factor K times epsilon naught. You can do the same thing with an inductor where the rather than the permeability of free space, this could go to some relative permeability that's some factor times mu naught. And this is the enhancement that you get from adding like an iron core. To your solenoid, to your inductor. And this can be, a pretty huge effect. Hundreds, thousands. And this has the impact of, boosting the inductance of your device. So let's look at a quick example where we take advantage of, so and actually just for completeness, then what this would become would be, mu r. If I can write a mu here. So we wouldn't have changed the dimensions or anything, but it would change the permeability, and so you would get an increase in the inductance. Where, mu r is, a lot bigger than mu naught. Anyway, let's look at a kind of a quick example here. So let's estimate the inductance of a spiral notebook binding wire. So, imagine you have a notebook and, it's got, and then along the edge of it, it's got that coil of wire, right? So we know that this is going to look like, this would have an air core. So it would be mu naught n squared area over the length. So I scrutinized a notebook and it had about 50 coils in it. And the dimensions of those coils, the area, well, the diameter of the coil is about 1 centimeter. And the length of this thing is about 25 centimeters. So let's put these ingredients together and calculate the inductance. So mu naught times 50 squared times the area is going to be 0.01, basically pi r squared. And then the length would be 0.25, just to have everything in meters and everything. And when we crunch those numbers, we find that the inductance would be basically 9.9. So let's just say 10 times 10 to the minus 7. So that would be 1 microhenry of inductance. And so you could imagine modifying this in different ways. Like, what if you took that coil and you have the same number of turns, but you compressed it together? So suppose instead of, like that, you squish it together so that it occupies only half the length. That wouldn't change n, but it would change length, and so you would get a boost in inductance. If length goes to length over 2, then the inductance would go from to 2 times the inductance. And you could imagine doing other modifications too, like if you had more coils, or the one that would have the biggest effect would be if you were to put an iron core or something in here. You could get a factor of 100 or 1,000 or whatever, depending on the material. And you can see that in one of the homework problems that asks you about that. So that's just a kind of a simple example of calculating the inductance for a solenoid, kind of our go-to system. And then we're not going to deal with doing circuits with this, with featuring inductors, although I suspect you'll encounter that in your subsequent courses. But just to give you like a rough big picture idea of where this would, what ingredient this adds. So consider now a circuit very similar to what we did with capacitors and RC circuits, but now we have added an inductor instead. So we have our inductor, our resistance, our voltage here, and so imagine this switch here closes at time equals 0. What you would see qualitatively would be very familiar compared to what you had looked at with capacitors, and that's that you would see the current, instead of the current uh, uh, starting at a large value and decaying like you would see in a cap, you would see the current build up. And the math of this would look very similar. It's this, charging exponential kind of characteristic. And then, if you then opened so that you discharged this, some later time, what you would see would be the current decay, very similar to a discharging capacitor. The difference, though, is that for this kind of circuit, tau, instead of being RC, is the inductance over the resistance. And so you could imagine, doing problems and stuff with that. And then kind of the interesting behavior happens when you take these components and you put them together in a circuit. So if you have a circuit that has capacitance and inductance, and you imagine like charging this up, and then suppose you charge this up, and you had some switch or something, and you close this, what would happen is you would get a competition between these effects. So with the inductor, you know that the current, it builds up in time, but with the capacitor, sorry, let me put it this way. So this is the inductor behavior, and with the capacitor, it goes like this. Sorry. You get what I'm getting at here. It goes like this, and so you have sort of a competition between these effects, and what this causes is this will be an oscillator. So this will cause the current will, flop back and forth between these two energy storage elements, and it's a way to make to make an oscillator. So with an electric circuit with a so that's hopefully that gives you a flavor for capacitors, or not capacitors, inductors rather, in kind of by using capacitors as an analogy. You can imagine, all kinds of applications and stuff you could do in circuits. We're not going to really get into that, but I just wanted to mention it. You can calculate the inductance for a solenoid. You can find the energy stored in an inductor, and you can relate the EMF to a changing current through inductance. So hopefully that helps with your homework and whatnot.